from the Center for Mathematics, Fundamental Applications and Operations Research, will tell us about the maths of the pandemic in Portugal, early days and current situation. Please, Professor Jorge.
Thank you very much. Since we are a bit behind schedule, I'll try to be very quick. I hope we are now seeing. Yes. So I think we are now seeing my screen. Yes.
Yep. Yes.
Okay. Okay. Very good. So I will try just speak about the mathematics of the pandemic in the following sense. I will speak about compartmental models, which Carlos and Toon have mentioned, and Nuno Rules have mentioned. Well, starting by saying that this sentence I like very much by George Buescu, which is all models are wrong, some models are useful, and this is exactly the case in which I will be talking now. So the most basic model for an infectious disease is the SIR model, which is about 1 century old, in which you have three compartments: the susceptibles, infected, and recovered people, and transition rates between these. So there are several assumptions for this model, which they're the most important of which is that the population is homogeneous. So this is a well-stirred system. This corresponds to what Nuno called the mean field assumption. Here we have no incubation period. And so this is really the simplest model you can think of. And what you get is a system of differential equations of this type. So you have the derivatives of the rate of change of each of the subpopulations, the susceptible, the infectious, and the recovered, and the corresponding rate of change. So this is really a very simple model. We could think of more sophisticated things, but this very simple model will be enough for the conclusions I want to draw. So here, beta is the transmission rate of the disease, because it is the rate at which individuals from this box travel into this box, and alpha, which is the rate of the rate of change from the infected to the recovered, is a parameter of the disease, and it is the recovery rate. If you think about it, 1 over alpha is the average infection time, because it is the time needed for leaving the infected box into the recovered box. We can think of more sophisticated models. For instance, this one is the simplest model, in which you have an extra box for exposed but not yet infectious patients. So it's the simplest model where you have intubation. This dashed thing, the dashed arrow, means that you want to include, maybe you want to include as well the possibility of reinfection. So you can really, or you can really make sophisticated constructions from compartmental models. But I will only look at the simplest one. So taking the simplest model for the outbreak of an infectious disease for which the immunity is 0 for a new infectious disease. Well, if you look at you have this system of differential equations. I will look at the second equation, this one, with, of course, the initial condition. The number of recovered are 0, the number of infected is I0, which is very small compared to the total population N. And so the susceptible are basically the whole population. And so from this equation, we obtain with the approximation then that ST is, the number of susceptible is the whole population. That is, IOT is small compared to N. We just replace S by N, and this becomes a linear equation which is integrated in this way. So basically, this is the equation which tells you what happens when you introduce a new infectious, contagious agent within a population wholly composed of susceptible. Basically, you will have exponential propagation. So if the exponent, if this exponent is negative, then the disease will die out. If it's positive, it will propagate exponentially. So rearranging terms, I'll just put and defining R naught like in this way. We can write this in this way, and here R naught is our well-known R naught, the basic reproduction number. So here it is clearly visible that its basic reproduction number is greater than 1, and then you will have exponential propagation. So initial outbreaks are always exponential. Okay, so what happened in Portugal? In Portugal, exactly, I have here the first 3 weeks of the outbreak in Portugal, from the 2nd of March to the 22nd of March. What you see is that it is an almost perfect exponential behavior, and the doubling period, this corresponds to a geometric progression of 32% per day on average, and which means that the doubling period during this time was 2.5 days, meaning that in 2.5 days, the number of infected individuals was double. So, I mean, having no intervention was not an option, because if you make the calculations and the SIR model allows for explicit solution, you would have a peak of infected. If you just let the infection run loose, you would have a peak about 1 to 2 million people, infected people, individuals at the same time, which is obviously impossible for the health system to handle. This would, if you have 1 million infected people, maybe you have 150,000 people needing hospitalization at the same time. So this is obviously impossible, and we had to break it first, and that is what happens with the lockdown. We flatten the curve. So flattening the curve means mathematically the following: you have this equation. And now you don't really have much control over alpha, because alpha is a parameter of the disease, the time of the recovery time, or the inverse of the recovery. So you want to lower beta, and that's what the measures do. I mean, you lower the transmission rate. So by lowering the transmission rates, what you do is that, if you recall that R naught was this, with proportional to beta, if you lower beta, then your RT, corresponding to R naught, but at time equals t, will be lowered proportionally. But now this, if you look at this is the same. I mean, if you lower B, you are lowering this product. So in a sense, this is the same as keeping B constant and lowering the number of susceptibles. So if you lower the number of susceptibles, you can make an approximation in this equation. And what happens is that the approximation turns to this one, this equation. Now, this equation is very well known. This is a logistic equation, which means that very well known from population dynamics, from biology, meaning that you will have not exponential growth anymore, but logistic growth, because you have limited resources. The resources depleted in this particular context are the susceptible. So what means is that this means that you stop having, you no longer have exponential pure exponential growth, but you have a logistic growth like this. And just as a rule of thumb, the inflection point here is halfway up. So the inflection point here is halfway up. So in a sense, when you detect an inflection point from the exponential phase to the logistic phase, when you detect the exponential point, you can look at the peak of the curve, so to speak. So this is what happens. This is a reconstruction of the infected, an estimate of IOC for the first wave between March and May. When I say estimate, this is not the number, the raw number from the CGS. It is it comes from BGS data on reported cases, and it calculates these curves, which are, we think, more accurate because unfortunately the recovered numbers are not, well, are not really reliable. So we have to think of a model of a modification to estimate this curve. And so what happens here is you can see that we really have an exponential evolution up to here, then an inflection point around the end of March, 31st of March, and then a peak in mid-April. And so here you have this in this curve, this nice logistic curve here. Okay, so I will now talk about very quickly about what is happening now. We take this curve, this estimate of IRT, to the data today. So this is what the number of estimated actors with our methods at the data today. You can see here this bump is the first wave. Here is this bump. So you see the difference between, and more worryingly, I mean, not only the deficit is enormous, but more worryingly, we still don't see any inflection point in this new exponential phase. This is worrying because, of course, if you see the inflection point, then you indirectly you can estimate where the peak will be. If you don't see the inflection points, well, there is really no limit on this curve that you can set a priori. So you really don't know where this is going to take us. This evolution is also seen by the new cases. At what we see here, the first wave, and then the long wavelength summer wave, and now this from the beginning of September, the second exponential wave. Carlos Antunes just estimated the present doubling period, which is 15 days. So the exponent is much slower than for the first wave, but this is still exponential in this, and it is already in a much larger amplitude than the first wave. So summarize the present situation, I would say following, we have an RT which is 1.2, around 1.2, and which has been greater than 1 since early September. This means, as I showed you in the formula, that we have an exponential wave, second exponential wave, whose doubling period is 15 days. The bad news is that we don't see any inflection points yet, and that we cannot speak of a peak for the second wave. There is no peak in sight. We hope that will be the case in the future, but at the moment we don't know where the wave will peak. And lastly, these exponential waves, I mentioned this earlier. I mean, the exponential means that the number of infected is very small compared with total population. So these exponential waves, you know, that herd immunity is far away. So in short, we really have to be resilient, and most likely the solution, long-term solution, will be in us. Okay, thank you very much.
Okay, George, thank you very much for your presentation. So now it's time to have a small recess.